There are many things that will dissolve in water that are not electrolytes. These are called the non-electrolytes. Non-electrolytes do not dissociate, instead they hydrogen bond to water. So we're going to examine these, and then we're going to see how is the solubility of both electrolytes and non-electrolytes and even gases affected by temperature and pressure.
If you have a compound that has oxygen-hydrogen bonds or nitrogen-hydrogen bonds, it can hydrogen bond to water, just as water hydrogen bonds to itself. We saw how ammonia can hydrogen bond to ammonia and how water can hydrogen bond to another water molecule. If ammonia is present in water, it hydrogen bonds to water because the nitrogen-hydrogen bond is polar enough to hydrogen bond to the oxygen-hydrogen bond in water. Here's an example of a picture of hydrogen bonding of ethanol dissolving in water. If you look at this up-close picture of the ethanol molecule, you can see there are two carbons with hydrogens attached. Those two carbons with hydrogens attached are very nonpolar, as we've seen. And if the entire molecule was just carbon-hydrogen bonds, it would not dissolve in water. That part of the molecule, the carbon-hydrogen part, is called hydrophobic because it does not want to dissolve in water. But part of this molecule has an oxygen-hydrogen bond, as we can see in this little picture here. The red is oxygen and the white is hydrogen. That part of the molecule is very polar and will hydrogen bond to water. You can see there's a dotted line from an oxygen in an ethanol to a hydrogen in a water molecule. That's not written in here, but there is a del negative on the oxygen and a del positive on the hydrogen in both molecules. The del negative on the oxygen in the ethanol will be attracted to the del positive on the hydrogen in the water. The hydrogen that is on the oxygen in the ethanol molecule can hydrogen bond also to an oxygen molecule, an oxygen in a water molecule. So there's more than one place for hydrogen bonding to occur on ethanol. In fact, there's two places for an oxygen to hydrogen bond to two water molecules. So there's a lot of hydrogen bonding going on with ethanol. Now, if you remember earlier, I said if there are no more than 3 carbons to an oxygen or 3 carbons to a nitrogen, it will dissolve in water. That's because there has to be enough hydrogen bonding ongoing to pull the rest of the molecule up in water. If there are too many carbons there, that amount of hydrogen bonding won't pull the rest of the molecule up into the water. Here's a picture of nonpolar dissolving nonpolar, and you can see the center is carbon tetrachloride, very nonpolar, and on the other side is octane. It's very nonpolar, and the two of them mix together quite easily because they have similar characteristics, like dissolves like. Dissolution reactions can have an energy change, and they can be either exothermic or endothermic. When some things dissolve, for instance sodium hydroxide, when you dissolve that in water, the solution becomes very hot. It is an exothermic reaction and heat is released. Hydrochloric acid is the same way. When you pour hydrochloric acid in water, you get a great deal of heat being released. But there are some things that are endothermic. For instance, if I put ammonium chloride in water, you find that as it dissolves, the solution starts becoming very cold. They actually use ammonium chloride in sports packs they have a way to break a little packet inside the ammonium chloride starts to dissolve in the water, and it starts getting very cool, and you can put this packet on a swollen ankle so as to reduce swelling. Sucrose is an endothermic dissolution also. If you ever take a sugar cube and put it on your tongue and let it dissolve slowly there, you'll notice your tongue starts to feel a little bit cooler. Or a piece of candy. Sometimes you'll notice how your mouth will cool off from putting candy in your mouth. We're going to start quantifying solution concentration right now. Solubility is defined as the amount of solute that will dissolve in a solvent. Now, it says here that we usually report it in grams of solute per 100 milliliters of solution. We define concentrations that way, but solubility, actually saying what's the maximum that can be put in to a solvent, we usually define that in grams of solute per 100 grams of a solvent. So you have to be careful and always read what it says and never assume that you know things, but look at the units to say exactly what does it say. Now, when we do look at concentration, not solubility, but concentration, we will be looking at the amount of solute in the solution, not in the solvent. There are three terms that we use in describing the concentration that are very loose terms. There are saturated, unsaturated, and supersaturated. Saturated means you've put the most in that can possibly be there. And that's usually what we define as being the solubility of a solute. How much is the most that you can put in? Unsaturated is anything less than that. And then supersaturated would be where you have more than the maximum. And that sounds like it's impossible, but it's not. And we'll look into that. As we increase the temperature of a solvent, solutes tend to be more soluble. This is not always true. There are some solutes that will be less soluble in water when you heat them up. Some examples are calcium and magnesium salts tend to be less soluble in water at high temperatures than at low temperatures. We see that evidence if you ever open up a water heater, an old water heater, you'll find inside there are solids coating the sides of the water heater and the heating element, and those are calcium and magnesium salts primarily that tend to come out of water as you heat it up, and so you know they can build up so much that your water heater stops functioning. That's what we call hardness in water. But in general, most electrolytes and non-electrolytes tend to be more soluble as you raise the temperature of the solvent. What we can do is raise the solvent to a high temperature and add lots and lots of your solid to the solvent. There'll be more than what you could add at a cool temperature. If we make sure all of the solid is dissolved at that high temperature and then allow it to cool slowly, you can make a supersaturated solution. Now, that supersaturated solution cannot be disturbed, nor can the container in which it's in have rough places, because the reason a supersaturated solution will form is there's no place for the crystals to form. As soon as you take a supersaturated solution and you take something like a spatula, or you drop in something solid into there, or there's a scratch on the side of the container, it will instantly allow all of that excess amount of solid that's dissolved to come crashing out as crystals. It's rather interesting to see in the laboratory when you do this. It's instantaneous. Now, something to remember is that gases do not increase in solubility as you increase the temperature. Gases behave differently from solid and liquid solutes. Gases have reduced solubility as temperature increases. For instance, if you were to warm up soda, you would find the carbon dioxide in the soda would more rapidly leave the soda, and it would go flat more quickly. Likewise, the behavior of gases is different from solids in that the solubility of gases changes as you change your pressure. What we find with gases is high pressure will cause greater solubility. That is why we have sodas pressurized, because we want to make sure that the carbon dioxide is dissolved in the water to give it the bubbly texture. Once we open a can of soda, we find the pressure is lower and the carbon dioxide starts escaping, and you leave it open after a while, the carbon dioxide leaves and you have a flat soda.